All right, I think this is a good time to begin. Um, so yeah, we're gonna continue with calculus. We were talking about squeeze theorem last time, a couple of the other main theorems. I skipped over some of the limit laws a little bit, but we're gonna use them today. So yeah, I'm not trying to cover every single page of the Stewart book, but I'm gonna try to cover all the main topics and then anything that's tangential or like topics that are probably you would take in a college class. I'm not going to cover every single topic of a college class, but yeah. Okay. So today we're going to be talking about difference quotients um, and derivatives. So this is like the main uh, part of the course, differential calculus, right? Derivatives, that's what we study. So lesson 8. Difference quotients. And derivatives. Right. So that'll be the topic for today, all right? The idea of a difference quotient really has its foundations in physics, um, dealing with speeds basically. So you're looking at, a particle moving in time and you look at its position usually. So maybe the x-axis is time, t, and you have some particle, let's say it's moving away from some point and this is its distance. Right, so here maybe this is the distance, the y-axis. Right, and then at every given point in time, the particle could be moving at a different speed or velocity, really. In physics, we'd say the velocity is like the speed, but it also has a direction. So it has the magnitude of speed, but there's also a direction component. So here, as the particle is moving at different points of time, it's moving at different rates of speed. Sometimes it's actually moving down in a downward direction. Sometimes it's moving up. But you can sort of figure out what the speed is or the instantaneous velocity of the particle by looking at what the slope of the tangent line to this curve, basically. So if you pick a random point, let's say here, and we draw the line that sort of only touches the curve at a single point, then this dashed line has some slope, and that's like how fast the particle is traveling in a particular direction at that particular time. But as the time changes, that velocity is also changing. It could be at constant velocity, but that's not the picture that I drew here. So this is like some particle that's maybe interacting with some force field, and as it goes through the force field, maybe it's like an electron or something, or a positron or a proton, and it's traveling through the field, and the field is obscuring its motion, and its velocity is changing as it travels. Right. So a common thing we might want to ask is, over some period of time, what's the average speed of the particle, or what's the average velocity of the particle, right? And if you want average velocity, then you're just going to be looking at how much the particle changed in distance and how much time it took for that change to happen. Okay, so let's draw another picture real quick. All right, so the main thing that we're studying in this topic is average speeds. And then we'll see that there's some sort of limit when we talk about instantaneous velocity. But let's just talk about average speed for a second. So again, we have the x-axis being time. This is some particle's position. Right, and let's say the particle starts like 10 feet above the ground, something like that. And let's say it travels kind of like a basketball shape, like a parabola, a downward parabola. So we want to know what is the average velocity, let's say from when the particle starts at time equals 0 to where it reaches its peak. Let's say it reaches its peak at t equals 2 seconds or something. Right? So the particle travels, and let's say this point here is 2 comma 15 feet. So basically it took this particle 2 seconds to travel from 10 feet above the ground to 15 feet above the ground. And you might ask, okay, so, what was the average speed of the particle? It obviously didn't travel in a straight line there, so there wasn't a constant speed, but there is some average speed. If you took the average and weighted it over all of the points, you would get some number, right? So here, basically, how long did it take to travel the amount of height that it gained? Well, we can kind of draw the rise over run from pre-calc or whenever you learn this. So it traveled it took 2 seconds to travel a height of an extra 5 feet because it went from 10 to 15, and therefore basically it's traveling at an average of 5/2 feet per second. Right, so this is your difference quotient. It's 15 minus 10. We take the difference of the y coordinates first, and then it's going to be an average speed, so we're going to divide by the how much x component, how much time it took for that difference to occur. So here it took 2 seconds. Right, and this is what we mean by a difference quotient. It's the difference, how much you gained in the y direction, divided by how much it took in the x direction to realize that change in the y direction. So here we get 5 divided by 2. Right? And that says that even though the particle wasn't traveling at a constant velocity when it traveled from here to its peak, it averaged at a rate of 5 feet per, or 5/2 feet per second. Right? And that's the slope of this line right here. So really what we're saying is, even though it wasn't traveling at constant speed, if it was traveling at constant speed, what would that speed be? And then if it was traveling at 5/2 feet per second constant, at a constant rate for 2 seconds, then it would travel the 5 feet. But of course it wasn't traveling at a constant rate. So the natural question in differential calculus is, instead of calculating an average speed over some interval of time, is it possible that we could calculate some instantaneous speed that the particle is traveling at a given instant in time, not taking into account any sort of interval of time, just like one particular instant, and that's it. So essentially, the derivative, which is this notion, is going to be a difference quotient, but the period of time that we're taking the average over is going to basically shrink to 0. We're going to take a limit, just like we were doing in the last couple lectures. So basically a derivative is just a difference quotient where the change in x is going to 0. So it's like an average speed over some infinitesimal period of time from now until now plus some really small amount of time, right? And what is the average speed over that interval? Okay, so it is a limit. So let's write down the definition of derivative. So it's very similar to this difference quotient where we're taking an average speed or an average velocity type idea, except instead of over a period of 2 seconds, we're going to be looking at the average velocity over like 0.0000001 seconds, and then take a limit as that goes to 0. Okay, so I'm going to write exactly that definition. Right, so the derivative of a function, if it exists at a point A, so the derivative of a function f at x equals a point is a limit as h goes to 0 of f of a plus h minus f of a divided by h, if it exists. Right, and we have to specify if it exists because this limit doesn't have to exist, right? And in which case, if the limit doesn't exist, then we would just say that the derivative does not exist. Right, and so this is basically a difference quotient where the change in x, now we're calling that h, and that's going to 0. So it's taking the value of the function at a plus h, so some shift by some small amount, minus f of a. So the value of the function after some infinitesimal time has elapsed, minus the original value of the function before the time had elapsed, and then divided by h, which is the how much time had elapsed, right? And we're letting the, so it's like the average velocity over some infinitesimal amount of time, and that amount of time is going to 0. And in that sense, it's like we're looking at the instantaneous velocity at the point A, since we're like really, really, really close to A, where it's f of a plus h, and that's extremely close to f of a when h is close to a. Of course, we would need the function to be continuous, but the thing we'll show in a second is that every differentiable function is also continuous at that point. So that's a nice little fact that we get. But first, let's go through an exercise. All right, just to check that we understand what's going on. So this is section 2.6 in the Stewart book. And this is number exercise 28. And they give us a function. So f of t is 2t cubed plus t. And they want us to find the derivative at any particular point A. So find f prime of A. F prime is just notation for the derivative of f at A. So there's this little prime, this little dash above the f, little line above the f. So find f prime of A. That means we want to find the derivative of this function at a particular constant point A, which could be anything, but we're just going to assume it's some constant, some real number. Right, and so we're going to look at the definition that we just wrote down again, and we're going to write it by definition. So this is the limit as h goes to 0 of 2 times a plus h cubed plus a plus h right? So that's f of a plus h. I just plugged in a plus h into the function, so just replace t with that. And then we're going to do the same thing, but just replace it with a. So now it'll just be 2a cubed plus a. And we're going to take this difference and divide it by h, which is the amount of time that it took. I just got to take care of something here. Okay, sorry about that. There's something in the chat that Some weird message. Okay, right. So here's our function, 2t cubed plus t. We want to find the derivative f prime at some point a. This is by definition f prime of a, so I plugged in a plus h into t here, into the function, and then I subtracted just plugging in a, and then I divided everything by h. And then it's just a little bit of algebra here, so we need to simplify this cubed part. So we need to like FOIL this out and then multiply it by a plus h again. But I already did that in my notes here. You can pause the video if later and try to do this on your own if you want. But yeah, so a plus h cubed, that just simplifies into, so this is a limit, so h goes to 0, 2 times, I'm just going to distribute the 2. So it'll be 2a cubed plus 6a squared h plus 6a h squared plus 2h cubed plus h plus a plus h minus 2a cubed minus a. All divided by h. All right, so a big expression here, but a lot of things cancel. There's a minus 2a cubed over here. There's a plus 2a cubed over here. There's a minus a over here, and there's a plus a over here, right? So these cancel, plus a minus a, plus 2a cubed minus 2a cubed, right? And everything we're just left with is 6a squared h plus 6a h squared plus 2h cubed plus h, all divided by h. And the h and the h here are going to cancel. They're going to divide to just give 1. Again, if you want to check this work and you're doing it on your own, maybe just pause the video, try to solve the rest of it. But I'm going to do the rest of it out right now. Oops. All right, I'll leave the ft. All right, so we had a couple things that canceled. Everything that was left was right here. We have 6a squared h plus 6ah squared plus 2h cubed plus h, all divided by h. All right, so we had a couple things on the top that canceled. There was like a 2a cubed, I think, that canceled with a minus 2a cubed, and then we had an a that canceled with a minus a. Right, and then now everything has an h, so we can just divide by h here. And this is like when we were solving the other rational polynomials, when we wanted to divide out by a number, so there was no division by 0 anymore. Here, as long as h is not equal to 0, this is our function. And this is equal to, I can cancel all the h's to get limit as h goes to 0 of 6a squared plus 6ah plus 2h squared plus 1. And then now we have a polynomial. A is just a constant. Remember, this is just some fixed number. And our function, our limit is a function of h, really. So here, as h goes to 0, this is just a polynomial in h, right? 6a squared plus 1 is a constant. This is some quantity times h. This is some quantity times h squared. So this whole thing is just a polynomial in h. A polynomial is always continuous at every point, especially at 0. So we can just plug in 0 for h, and that's our limit. So these two terms in the middle cancel, because those are just times 0. And this whole thing is just 6a squared plus 1. And that's our final answer. So this is the derivative at an arbitrary point, a, of this original function at the top, f of t equals 2t cubed plus t, when we take the derivative at a particular point a, we always get 6a squared plus 1. And later when we talk about the power rule, that'll be an easier way to solve this problem. So the power rule will say that you just pull this 3 down, multiply by the 2, you get 6, subtract 1 from the exponent, and you'll get 6a squared plus, and then the derivative of t we'll be able to show is just 1. So yeah, once we get the power rule and we show that derivatives are linear, then this problem would be a lot easier. But here we're actually like brute force solving it from just the definitions. So I would say this would be basically like the hardest way to solve this problem, but since we're just being introduced to derivatives, this is just explicitly using the definition of a derivative and showing what the function is, the derivative function of the original function is as a function of a. In this case, it's just 6a squared plus 1. Okay, so that's the derivative of this function. That's problem 28. If anybody's watching, are there any questions? Another spam in the chat. Okay, right. So here, this is kind of hinting at a notion that the next section in Stewart talks about, where you can think of the derivative as sort of like an operator where it's sending functions to functions, but sometimes you lose some points if the function, sometimes functions they don't have a derivative at any, at particular points, or maybe they don't have a derivative anywhere, right? In this particular case, we had a function and its derivative was defined everywhere. So in this case, the derivative actually is acting as an operator that sends functions from real numbers to other functions from real numbers to real numbers. And in linear algebra, we would call that an operator on the linear space of functions. Right? So I'm just going to write down that idea. It's kind of important here. Maybe I'll switch to black marker here. Okay, so yeah, just the first point, the derivative acts as an operator and this sends functions from real numbers to real numbers to itself. Except there's a little caveat here. There should be like a little asterisk here that potentially we might not be left with the entire real numbers as the domain, because the function may start out from the real numbers to the real numbers, but the derivative of the function may no longer be defined at all points, or possibly might not be defined anywhere, right? So I'll put acts here in sort of quotes. But assuming the function is differentiable everywhere and the derivative is in some sense smooth enough, then there's this whole notion of C0 function, C1 function, C2 function, where this operator actually makes sense, where the domain is not shrinking when you take the derivative, right? So some functions have derivatives at all points, like polynomials, for instance. Some functions, like the absolute value, have no derivative at particular points, and other functions, they might not be even continuous anywhere, so they're definitely not going to be differentiable either. So you have this whole array of functions. Sometimes they have derivatives at all points, sometimes just some subset of the original domain, and sometimes they don't have derivative anywhere, right? But yeah. But if it's a nice enough function, then sort of this makes sense here, and we can say that it sort of acts as an operator that sends functions to other functions, which we call the derivative function. And then you can take the derivative of the derivative, that would be the second derivative function, right? So like the one we were just looking at, let's write that as an example for our notes. Right, that one said the original function was f of t, and it was 2t cubed plus t. And we said when we took the derivative at an arbitrary point a, we got 6a squared plus 1. So if we plug in t for that, we can sort of say like the derivative function at t is itself a function, and it's the function 6t squared plus 1. And then we could take the derivative again. I'm not going to prove this, but you could take the derivative again using the power rule, which we'll talk about probably next time, but you could take the derivative again and you'll get 12t. So we start out with a function f of t, we take the derivative, we get a new function, which is also a polynomial in this case, which is 6t squared plus 1. Then we could take the derivative again, we got 12t, and we could actually take the derivative again and we would get 12. And one more derivative, we would get 0, and then it would just go 0, 0, 0. So this actually shows something interesting, that if you take the derivative of a polynomial, you actually end up with a different polynomial. And the degree is always 1 less than the polynomial that you started with. So that's a very interesting fact about calculus, that derivatives of polynomials are very well behaved. In fact, they're operators from polynomials to polynomials. You take the derivative and it just lowers the degree by exactly 1 every time. All right, so these are examples of functions where you can take the derivative, and the derivative is actually defined at every single point that the original function was defined at, and then you could take the derivative again, same thing. But sometimes, like I was saying, the function may not be smooth everywhere, or may not be C1, like we would say. And in that case, there may be points where there is no derivative. So let's do an example of a function that has no derivative at a certain point. Right, and that's the one we've already talked about. It's the absolute value function. So this is f of t is equal to absolute value of t. In this case, the derivative is defined on a subset, but it's not defined on all real numbers, because I think possibly another time, or maybe we didn't show it, but we said it, that the derivative does not exist for this function at 0, right? So f prime of t is a new function. So we do get a new function, f prime of t. It's just that it's not defined on all real numbers anymore, because in particular there's no value at t equals 0. There is no limit. There's no difference quotient. The limit of that difference quotient at 0 doesn't converge. So there is no, actually the left limit and the right limit are different. So in this case, the left limit is -1. So the derivative of the function is actually -1 if x is negative. So this is a piecewise defined function. It's +1 if x is strictly positive. And then the function's actually undefined if x is exactly equal to 0. So we start out with a function. It's defined, the domain is all real numbers. We take the derivative and we get -1 for all of these values. We get +1 for all of these values. And if we try to take the derivative at 0, there is no limit for that difference quotient. And so we say that the derivative is undefined there, or we just say that the domain of the function shrinks and there's no 0 allowed in the domain anymore, because the limit doesn't exist for 0, so we say the derivative doesn't exist at 0. Okay? Any questions? So derivative is an operator. It sends functions from real numbers to themselves. except possibly we get a domain that shrinks based on whatever points that limit doesn't exist at. In which case, those points we say that the limit doesn't exist or the derivative doesn't exist and the function is not differentiable at those points. And then the notion or the intuition for those points is that there's some sort of sharp change in the trajectory of the, if you're thinking of it as a particle, the particle is moving in one direction, and then at that exact instant, it abruptly changes direction. So if a function is differentiable, it sort of has to change direction in a smooth, continuous way, and it can't have these sort of, for the absolute value, it at 0, it's going straight down, and it never sort of slows down before it starts going back up. It just immediately starts going back up. And so on this part of the curve, the slope of the tangent line is -1. At this point of the curve, the slope of the tangent line is +1. But at 0, there's sort of no way to make sense of the limit, because if you look at the difference quotient on the left, the limit is -1, and on the right, the limit is +1. And therefore, since the left and the right limit don't match, we say that the limit doesn't exist. Right? That you can't have a left limit and a right limit that are different, because the limit, if it exists, the limit, it should be going to a single number. There can't be two different numbers. Okay, so it's undefined at 0. There is no derivative for this absolute value function at 0. It just abruptly goes from a slope of -1 to 1 without any sort of, smooth change. Right? All right, and then the last problem we're going to look at, well, it's not really a problem, but it's a theorem in the book, and it's a very interesting theorem. I'm going to write down the proof here because it's not too difficult, and I think the proof is very good for elucidating or illuminating what is going on with these difference quotients and limits. Switch back to red. All right, so this proof is in the book, in the Stewart book, the calculus book, page 151. And this is a theorem. And the theorem says that if f is differentiable at a point A, so if f is differentiable at a point x equals a, then, importantly, if it's differentiable, then it's also continuous at that point. And again, to remind you what continuous means, it just means that the limit as x approaches a is equal to the value of the function at a, or is equal to f of a. So here we're assuming that a particular limit exists at x equals a, which is the definition of differentiable, and we're trying to prove the second statement that I just said, which is that the limit as x approaches a is equal to f of a. So we're assuming some limit is true, and then we're trying to prove some other limit is true from it. So really we're saying that continuous is less strict of a notion than differentiable, meaning that if you're differentiable, you're automatically continuous, but just because a function is continuous doesn't automatically mean that a derivative exists at that point. So just because a function is continuous at a point doesn't necessarily mean that it's differentiable, but if it is differentiable, then it's definitely continuous. So that's a very important idea for this problem, right? So that's how we want to prove this. We want to assume the limit in the definition of differentiable, and we want to prove the limit in the definition for continuous, for a continuous function. Okay, so that's what I will do now for you. All right, and again, you can pause the video if you need to look at the statement or think about it a little bit more. Okay, so here's the proof. We're going to, like I said, we're going to first assume the limit exists for the derivative. So assume f prime of a exists. That's exactly this limit. There's actually two limits in the book that are equivalent to each other. I'm going to use the second one. So instead of h going to 0, you can have x go to a, and then you just have to do kind of like a change of variables. It's just a translation. But so assuming that f prime of a exists means that the limit as x goes to a of f of x minus f of a over x minus a. So here x minus a is what we used to call h before. So now we have f of x instead of f of a plus h. So we're assuming that this limit exists. It's equal to L. And now we want to prove that the limit as x approaches a of f of x is approaching f of a. So we're assuming that this limit holds, and we want to show that the limit that defines continuity is also satisfied for f. Okay, so what we do here is we're going to multiply by another limit that we know exists, which is x minus a as x goes to a. So basically, I'm going to multiply both sides by x minus a, and we're going to use the product rule for limits to say that when I multiply x minus a over here, I can actually break it into a limit and move that limit to the other side. So here, this is basically equal to L times a limit as x goes to a of x minus a. Right, but the limit as x goes to a of x minus a, that's just a polynomial in x, right? A is a constant, so as we can just plug in a here, but a minus a is 0, so this whole thing is 0. Any number times 0 is 0, right? This is multiplication here. So the limit, whatever that limit was, times 0 is 0. And so now we have the limit as x goes to a of f of x minus f of a is exactly equal to 0. And now we can use the limit laws for sums to move the f of a to the other side. But the limit, as you know, f of a is just a constant, so the limit of that is just f of a. And so really here now we're saying that the limit as x goes to a of f of x is actually just exactly equal to f of a. And that's it. So f is continuous because as x approaches a, the value of the function f of x is getting closer and closer to f of a. So the function has continuity to it. As I get closer to a particular input, the output is getting closer and closer to the output at that point. Okay, so just one more time real quick. We assumed that the derivative exists at a, which was this limit by definition. We assume that it exists and it's equal to L. We multiplied basically the top and bottom by the limit as x goes to a of x minus a, which does exist, so we're allowed to break it apart using our limit laws. The limit is just 0. So when we multiply both sides of the equation by it, we get on the right-hand side, the x minus a's cancel on the left-hand side. We get 0 on the right-hand side. We get L times 0. And then we get that the limit of this difference is 0, and therefore the definition of continuity holds. So yeah, that's the proof. If the derivative at a exists and it's equal to L, then necessarily the function is automatically continuous at that point. And it doesn't matter what the derivative is. L, you can see no matter what L is, it always gets multiplied by 0, and this whole thing is always just 0 on the right-hand side, which means that this limit always holds. Okay, I think that's basically all I prepared for today. Um, right, so we did a little bit on derivatives. Next time, I'm probably going to get into some more of the derivative laws. Let's see where we go in the next part of this book. Yeah, so we're in 2.7 right now. That's talking about the derivative as an operator that sends functions from real numbers to real numbers to itself. They talk about higher derivatives, which I kind of mentioned briefly. Right, I think that's about the end of the chapter. Yep. Yeah, and then in chapter 3 they go into differentiation rules, and that's your sums, sums of functions. If you want to take the derivative of that, it's the sum of the derivatives. If you have a scalar multiple of a function, and you want to know the derivative of that, it's just the scalar multiple of the derivative. So that's another way to say that the derivative is a linear operator. We said before that it's an operator, but it's actually more than that. It's a linear operator, so it has linearity properties, which makes it easier to take derivatives of functions that are I got ahead of myself. That are combinations of functions, such as sums of functions, products of functions, and then later we'll have more rules for, the ratio of two functions. If you take f divided by g, and also compositions of functions. So there's something called the chain rule, and that tells you that if you have an f composed with g function, and you know the derivatives of f and you know the derivative of g, then how do you find the derivative of f composed with g? Right, and that's called the chain rule, and that's a theorem, so we'll probably prove that next time. Yeah, so sums of functions, we can take the derivative. It's the sum of the derivatives. Scalar multiplication works nicely. Products of functions, division of functions, compositions of functions, and that covers like a lot of stuff. So after we do all these differentiation rules, you won't have to work out all these problems by hand. You'll just be able to sort of break the problem into a series of derivatives. You can break it into, some composition of functions or some sum of functions and find the derivatives individually. And yeah, that makes finding the derivatives a lot easier. Okay, so that's it for today's lesson. We'll be back on next Tuesday with more calculus. Okay.